Okay, so we've had our short business introduction to segmentation and the sort of things you can do with segmentation. Now we're going to implement some segmentation in the exercises. Now, just a few points. The examples I give in the exercise, they're kind of pretty simple with a small number of items. I actually have an exercise 4 in the notes, which is actually quite a complex large-scale customer segmentation exercise. I actually set that in the homework last year, but it was a little bit of a step too far, and it kind of caused quite a few people to drop the class. So I'll maybe go through that exercise later, but for the moment we just have some very simple segmentation. So let's get the directory. Now let's read in the car data, and I'll just explain what we're doing. Now let's just have a look at the car data. And you can see we have different brands of cars, and each of them has been ranked, kind of rated by different consumers. It's not a ranking, it's a rating by different consumers on 6 different scales. And I think what happened here is that multiple consumers rated these cars, and then we had the aggregate value. But in reality, this is just a very simplified data set which we can use to help illustrate the ideas of segmentation. So what we want to do is we want to, from a marketing perspective, we've got 10 different brands, and we want to work out which brands are competing with each other. Now, again, we probably have an idea here. Again, if this is a commercial data set, it would be a lot larger. But we can imagine that the high-end cars, such as Mercedes and Lexus, are probably competing with each other. And also maybe the lower-end cars, such as Ford and Chrysler, are also competing with each other. Okay, so let's just see again what's in our data set. And you see we have the names, and then we just kind of have all of these integer values. So let's kind of go back to our code. And the first thing we're going to do is to check competition. Is we're going to create a series of scatter plots. Now, par MF row. All this does is it splits the graphic screen into 4. So MF row equals C2, 2. That's just saying 2 rows, 2 columns. So, I mean, this is just code that you learn. And if you say, and then you say want 3 rows and 3 columns, it would be 3, 3. So that splits up my graphic screen. Now we've already covered the plot command in the first week, and this just basically says we're going to plot exciting on the x-axis and safety on the right axis. We're going to give the name of the plot using main. We're also going to have PCH is we're going to use that's kind of the cross symbol. And we're going to give labels. Now, the plot command actually is defaults when you just have 2 continuous variables. It will actually default to a scatter plot. And then we're going to actually add some text, and we're just going to add basically the coordinates of exciting and safety just offsetting a little bit. We're going to put the brand labels, which is in the brand column from the data. And we're going to do this 4 times, and we're going to have 4 plots. Here we are. So we have on these different dimensions. So here we're doing our 2 segmentation bases. These are exciting and safety. Here it's luxury and family. And here it's sporty and practical. And here it's luxury and practical. And I'm going to interpret this in just a minute, but you see a bit of a problem. Whoops, we've got some labels on top of each other. Now, in fact, ggplot could actually do this in a much more sophisticated fashion. Besides ggplot, we're going to use a library called ggrepel, and it's named after what it does. It creates labels that kind of repel each other, so they're not on top of each other. And let's just have a look at what we do here. We have ggplot, and again, ggplot has this common syntax we covered last time. You put in your data set, then you use the AES command and what columns you're going to actually use. Then we use geom_point, which is what creates a scatter plot. It does a series of points. Theme BW, this is just me making it black and white. ggplot defaults to gray. And then geom_label_repel just is from this extra library, and we put label equals brand as before. So we create 4 plots and we call them plot 1 to 4. Now, just if you thought things were a little bit too simple, with ggplot as a different way of arranging plots than the standard plot. So we can't use the par equals mfrow. We've got to use something else. And we use a library called gridextra. And if you're regretting taking this class at this point, I don't blame you. We do grid, and we have a command from gridextra called grid.arrange, where we do plot 1, plot 2, plot 3, plot 4. And this time we set the number of columns. Obviously, if we have 4 plots and we have 2 columns, then we have 2 rows. And there we go. We have something much nicer. Now, you see here that on the most exciting car is the Porsche, and the safest car is the Volvo. And most of these middle market cars are somewhere in between. If we're looking at sporty and practical, we can see there's this kind of segment of cars that are Chrysler, Ford, Volkswagen, Volvo, and Jeep, which are pretty practical and not very sporty. And we have BMW and Porsche, which are maybe a little bit less practical and a lot more sporty. And then we have these mid-market cars in between. Now, you do see some similarities between these plots, but they're not exactly the same. And let's just think about these number of plots. We've got 6 different features, and we're going to choose plots with 2 of these features. How many plots do we have? That's my little challenge. Okay, so we're choosing. Let me get my pen, which seems to have broken. So just let me pause the video and I'll get that working. Okay, so apparently the trick was I just needed to unplug and replug in my my pad. So we have 6 segmentation bases. So we'll just say we'll actually call these guys features, which is what the data miners use. And we need to choose 2. And if we choose 2, how many? So I'm going to ask you, how many different scatter plots? And the answer is, do you guys remember this from pre-calculus? 6 chosen from 2 equals do you remember this? Which is equal to 15 scatter plots. Don't worry, I'm not going to put this on the exam. So recall, it's going to be n minus n factorial. This guy here is r factorial. And this is n minus r factorial. Okay, guys. So now just think that if we have 100 dimensions, then how many we're actually going to get. So let's just think. equals 100 times 99 equals 99. We have nearly 10,000 different scatter plots. Now, if I'm a marketing researcher or whatever sort of, researcher I am, I can't be like looking at a page of 10,000 scatter plots and thinking, whoa, I can get some meaning from this. So what we do is we're basically going to do a technique called dimensionality reduction. And imagine we have basically our data here. So we have, let's just say we have our data, which is, it's got n rows and m columns. We're basically going to kind of take the maximum. We're basically going to take the maximal variance. We're going to take n rows and k columns, where this will usually be 2. And we're basically the maximum amount of variance in the data that we can fit into these 2 columns. And the technique is called PCA, or principal components analysis. So for this class, I put a little bit of the math on the notes for you to look at. And I linked to an article that is a really good description of the math. I also might put some mathy notes for the industrial engineers in the class, but don't be scared by those notes because you won't have to know them for the exam. Just literally think we've got a lot of information, we've got a lot of columns, and we're just trying to squash as much of that as possible into a smaller number of columns, say 2 columns. We're trying to squash as much information as possible into these smaller number of columns. That's PCA, or principal components analysis. Okay, so let's run with principal analysis. Now, ARP has about, in between the base package and some extensions, ARP probably has like about 20 different ways of doing principal components analysis. Plus, if you know the math, it's actually pretty easy to do it yourself, but that's a little bit beyond this course. So what are we doing? We run a function called printcomp, and we're kind of going to send the card data. Now, note, we don't send the first column because that has the labels. So it's basically all rows, columns 2 to 7, self-explanatory. Now, scale. Now, what scale does is, say, for example, one of my columns was wages from 0 to say 200,000, and the second column was time per day spent on exercise. Yeah, so that's a maximum of 24 hours. Then obviously the 0 to 100,000 would actually predominate. So all scale equals true does is it basically normalizes the columns. And it does what you do in your stats 1, stats 2. You subtract the mean and you divide by the standard deviation. That's all it's literally doing. Now, in this case, we don't actually have to scale equals true because all our columns are on exactly the same scale from 1 to 7. Though there's arguments in that instance whether you should scale or whether you shouldn't scale, but we'll leave that for the moment to avoid complicating things. So let's just run the principal components analysis. Now let's do names. Whenever you have an object in R, names tells you the kind of the sub-objects. So we have the sub-objects, and I'll tell you a few things which actually are in there. So the center tells us the means of the original variables. And stdev actually does exactly the, whoops. I guess because we scaled, it's not actually bothered giving us the standard deviations there. So that's the principal components analysis. Now, the X is probably the most important thing in the principal components analysis. That gives kind of the new derived data. So the new derived data, what this is principal components 1. So just go back to my little analogy before. Principal components 1 is squashing as much data as you can into this one dimension. Now, of the remaining information in the data, principal components squashes as much of the remaining data into that second principal component. And this carries on and on and on and on. But the first two principal components basically have the maximum amount of variance you can get within 2 dimensions. So let's plot this now. So what we're doing, we're basically creating a new configuration, and cbind is just we're putting columns together. So we're putting the first column of car data, which is the brand names, along with the principal components. Yeah, so we can actually, that just means we can do a plot. We've got the labels and we have the new kind of the new configuration there. So now let's plot it in ggplot. Very simple ggplot, exactly the same as before. This time on the X we're plotting the first principal component, and this time on the Y we're plotting the second principal component. And here we go. So this is based, kind of just think of it like as a combination of all of your scatter plots. And you can see here on principal component 1, Ford and Chrysler are very similar to each other, which is similar to Jeep. So again, from a brand competition angle, we can see which brands are competing with each other based on consumer perceptions. We can also see Mercedes and Lexus, you know, which brands are competing with what they are competing very closely with each other. Volvo's a little bit on its own. Saab and Infiniti are mid-market. And you see BMW and then Porsche kind of almost extreme in one direction. So how much information does this contain? Well, again, we're not doing the matrix algebra, so I'm not going to explain like what eigenvalues are. I can't really, because it's related to how we do this with matrices. But what I will tell you is very important. There are things called eigenvalues which tell you how much variation are actually available in your data. So we have a function called getEigenvalue, which is in the Facto Extra library. And this does this kind of simply. Here we are. I'm not sure why we went over 2 columns before. So we have basically, and this is very important, this will definitely be on the exam. So this basically is telling us the first dimension has basically 72% of the variation or information in the data. The second has almost 18%. But together, they have almost 90% of the information in the data. Now, the higher the percentage, the better. But at the same time, if I've got the original data with 100 dimensions, I'm not going to get 80 or 90%. It's just not possible to squash all that data into 2 dimensions. Now we're going to do the loadings. And again, as we're not doing the matrix algebra here, you're just going to have to trust me on this. This is basically just what we call the rotation matrix. This kind of works out the relation between the new principal components we're showing here and the original variables. And we also have to, what I'm doing here is we have to scale that by the standard deviation. So the math, don't worry, this is just going to have to be a copy and paste job when it comes to the code. And but again, you need to know the interpretation of the principal component loadings. And this is basically just the correlations between the original data and the new data. Now, what you would do in a marketing context is you would actually try and give a name to the new dimensions you've got here. Now, I remember from previous years is that the accounting students hated this because this is just not very kind of definite. We're trying to be a bit artistic here. We're trying to think of names for our dimensions. So let's have a look at the first dimension. It's high on family and practical, but it's low on sporty and luxury and exciting. So I'm always going to call this the staid dimension. and Chrysler is high, and Ford are highly stayed, but Porsche is not very highly stayed. It's like in the opposite direction. Now again, there's no real meaning to the direction. You could flip this around if you want, and you could maybe have, you could do the minus of this, and you could have, call it exciting. You could call it the sporty exciting dimension. You could have Porsche at the opposite direction. The second one is a little bit harder. It's high on safety and luxury, so we're almost going to call it the kind of the high-end family car dimension, or something like that. So we have the Mercedes and Lexus high, and then the Saab and the Infiniti, and then things that aren't kind of high-range, you know, luxury family cars. The Porsche is a bit too exciting and doesn't have probably much kind of interior capacity, and Ford and Chrysler are probably lower-end cars. So that's my explanation of it. So again, in the exam, I'm going to give you one of these, and you're going to have to interpret the dimensions. Now let's just reset the graphics, which I'm going to do before the biplot. Now the biplot, this is interesting. It will take, basically I've got the car. Basically all I actually send it the original PCA. Whether or not I'm not going to scale, I'm not going to scale here. And then I send it the labels from the original car data. And what do we have here? Well, what this does is the previous loadings I showed you, it kind of relates. We have the PC1 and the PC2, and it shows the loadings as vectors. And, you know, where these fit relative to the original dimension. So we have the original luxury dimension, and we can see Mercedes and Lexus is close to this. We have the sporty dimension, and exciting. You see BMW and Porsche are off the charts here. And we have the practical, and we see that Jeep, Ford, and Chrysler are practical cars. And then we have Volvo somewhere between family and safety. So again, this is just almost another marketing tool to actually relate your original data to the new visualized PCAs. Now, this I had in the notes. This is like optional material I put in the notes. This is not going to be on the exam. Now, you might not like the interpretations, so you can actually rotate your solution. And again, it's rotated by matrix algebra. We're not going to cover in this class. And what we're going to do is we're trying to rotate it so that you have either very high loadings or very low loadings, which makes it much easier to interpret. So let's just do, we're going to run a type of rotation, which is a varimax rotation, which is basically just trying to maximize the variation on each of the loadings, and it does this by either setting them to 1, close to 1, or 0. So we're going to run the varimax rotation, and we're going to get the loadings. And again, this is not going to be on the exam. This is not going to be on the video. So if you really don't like this, you can forward. And you see here we have the new loadings. And you can see here that now we have the new dimension, which has minus luxury, minus sporty, practical and family, and minus exciting. So it's close to the original, but you see safety is 0. And you see that safety is very highly loaded on the second dimension. So it's just trying to make the solution easier to interpret. And again, this requires a little bit of matrix algebra, which we're not covering, so you're just going to have to take it from me that I know what I'm doing. And we have the rotated solution here. And so what we're going to do here is we actually should probably give it some names. And then we're just going to do another scatter plot of the new rotated solution. And you can see it's very much as before, but, you know, maybe the dimensions are a little bit more interpretable. You know, you have this kind of almost going from highly practical or maybe low-end family to kind of high-end up here. And then you have the staid and safety Volvo, Mercedes, and Lexus, all down to a very exciting sporty car down here in Porsche. Okay, and just a note, and I'm not going to really cover it, the psych package also has a lot of rotations, and they do, you could actually read the, just kind of Google psych R, and you can read documentation on this, and they do lots of kind of variants of this.